welcome everybody to today's webinar. My name is Dan Combest, and today I'll be talking about simultaneous simulation and post-processing within HELYX. As always, I try to state the webinar goals, and the first one's always introducing ENGYS CAE innovations. Next, I'll talk about how data analysis plays a role in CFD in a very broad sense. And then I'll introduce some of the post-processing features in HELYX and elements. As always, I'll wait to answer questions until the very end, and we can continue via email post-webinar. So for that invite, you can just hit reply and it'll go directly to me. If you're already a customer of ours, you can just write an email to support, and either a support engineer will respond with an answer, or I can take a look at those and help answer those questions. Today, I'll start with just very broad discussion of data analysis in CFD. I'll talk about primitive and derived data, probe data, integral data, multidimensional data, kind of things that if you're a seasoned CFD engineer or researcher, that you'll have a fairly good grasp on. Then I'll dive into the HELYX View Tab. This also applies to elements. Then I'll talk about how this is all kind of pulled together in Runtime Visualization. I'll leave you with a few take-home messages and then answer questions at the very end. So while I was making this, either I had too much coffee or too much time to think about this, but I think at the end, a broader sense that I was left with is that we tend to optimize effort and value. Okay, I remember this in graduate school with how much effort it took to set up a simulation or to obtain a result, and really how valuable that was. So if something took weeks to do and it was not very valuable, then I really just kind of didn't even focus on that. So low-hanging fruit that are high value are things that we tend to optimize, or we tend to try to strive towards. And if there were more descriptive simulations that were easier to obtain, I think we would really rely on them more. So these are kind of two thoughts that I wanted to carry out throughout this discussion today. And when I say more descriptive simulations, I don't necessarily mean just more physics, more features. I also mean simulations in this broader sense of being able to extract data, which we can use for our own designs. So let's start at the beginning. So CFD analysis has many different stages. There are challenges within each one of these. So starting with geometry import, actually we can go even before that for the geometry creation. But let me start with geometry import, surface manipulation, mesh setup, simulation setup, the actual simulation, the post-processing, and then taking these results and interpreting them and applying them back towards our designs. So overall, for a given geometric state, or for a given operating point set of boundary conditions for different physiochemical properties, for a different initial state, we seek to really evaluate data. I went very broad here. Sometimes we would say evaluate performance, but evaluate data at a specific point in space, over integrated boundaries, within multidimensional space. So multidimensional could be X, Y, and Z, and also in time. And we do this for a variety of primitive data, so things that come out of Navier-Stokes or momentum equation, and also derived data. So we're looking at vorticity or Q criteria or pressure coefficient, something like that, lift and drag coefficient. When I talk about primitive and derived data, some very practical examples of things that are important during post-processing. Here's an example right here on the left of mean near wall velocity. So this is from a transient simulation using DDES. And the near wall velocity is actually even though we're using a no slip boundary condition, the near wall velocity is the velocity of the cell just above that no slip. So we're able to interpret kind of the velocity behavior very close to the wall, just above that no slip. And this is a example of primitive data that's been averaged. And then over here on the right, we have a pressure coefficient over a vehicle. Now this gives us lots of information about where drag or thrust is being induced, or lift or downforce. So we're given a lot of information just from these two different plots about the aerodynamic performance and behavior of our particular design. So in reality, we need tools to be able to analyze primitive data and to actually create derived data within user-defined, generic, or specific operations, and then also common derived data output for things about fluid characteristics. So vorticity is a kind of a fluid characteristic, how much swirl is happening, aerodynamic evaluation, lift and drag, acoustic modeling, and maybe heat transfer evaluation, so heat transfer coefficients. We also need to be able to enable time averaging of transient data. And this is all really achieved inside of Helix and Elements with things that are called field manipulations. So here's just a very brief list of these generic operations we can apply to primitive data or derived data, and then very specific operations that are related to different actions and different data that we'd like to generate during a simulation. For example, Proudman sources if we're looking at acoustic modeling, or even total pressure coefficient, something like that. Okay, so we talked about primitive and derived data. Now actually interrogating our simulation, probe data, this is typical data that is compared to experimental results. So temperatures, pressures, velocities, these can be at steady state, these can be transient fluctuations. For example, here is a project that we did a few years ago that was a transient simulation in a compressible flow, and we're looking at the acoustic performance or what's happening as this flow exits this muffler. So flow comes in, goes through this device, and exits. And so we're capturing the performance of the flow or the activity of the flow on a domain. So right here is where that small muffler that I was talking about. But here we have a much larger domain, and we're collecting probe data and comparing that to experimental results. So it's not simply just, here's a pressure value. There is some post-processing involved with that. So probe data can be a little bit more complex than just looking at one single value. And typically these are very easy to set up, and they require some effort by users afterwards to actually apply and interpret that data. All right, integral data. This is data that is integrated over a surface or throughout a volume. And this really gives users the capability to really kind of contract complex data into something that's meaningful for design input. And when I say contract, we're talking about summarizing or averaging over data or over surfaces, or summing up over a surface. Lift and drag data is a great example of this. Forces, moments, turbo performance. So turbo performance would give us information about how much power or efficiency a particular fan may have in a device or a pump. Surface reports are something that I use on a regular basis, and this gives us the mean, the max, and the min of a particular primitive data type or derived data type over a surface. So we'd be able to get average pressure on a patch or average pressure on an outlet, and we'd be able to see the min and the max. Next, we have volume reports, which gives us the min, the max, and the mean of a variable over space. Now, these are great in terms of evaluating our simulation health, and it gives us this reality check of, are our simulation results valid or meaningful? Do we have speeds within the simulation that are much higher than we actually see in experiment? It gives us this kind of sanity check capability. And overall, I think integral data is the most descriptive for the cost and effort. For example, here we have a front lift coefficient. This is a transient simulation, and we're able to actually capture this over time and then further condense that data, contract it down to an average value over time, and really give us a great perspective of performance of that particular vehicle design. Next, we have multi-dimensional data. For multi-dimensional data, they're very complex. So three-dimensional, if we left it in its raw form, it's essentially meaningless. I mean, we have this cube, we would only really see the boundaries of our mesh. We can't really peer into it and see what that three-dimensional time-dependent data can give us without doing something like applying a filter. So filters are used to prune data. And I don't mean prune data in a bad way. I mean prune data in a way to communicate a relationship. So slices will condense dimensionality. So at this plane, at this hub height, what are we seeing these vortices shedding off of the front of a vehicle? Or we can see these jets of velocity coming out of a certain duct in a vehicle, or we see tip velocities, something like that. So slices and clips really condense dimensionality. So it takes this very complex and lets us complex 3D data and lets us peer into something of lower dimensionality. Streamlines really communicate motion. That's really the purpose of, if I place something here and I see, it's able to show us exactly how that flow would react if we release some sort of tracer at a certain point. Glyphs also communicate motion. I personally like streamlines better than glyphs just because they help connect a starting point to an endpoint much more strongly. Also, data threshold. This is for further pruning, and then ISO surfaces. It really helps us isolate similar data. So if we're talking about chemical reactions, maybe it's at an equimolar mixture isosurface. If we're looking at vorticity, it would give us different isosurfaces give us different points in space that are at the same vorticity. And this in itself is an inherently visual process that requires input. So this is where human judgment comes into play. We can try to non-dimensionalize this data, and if we know the range of values ahead of time, then we can really do a lot of this ahead of time without interacting. So all of this setup can actually be done within Helix and Elements on the View tab. This is particularly interesting because it does take a lot of input from users. So let me jump into talking about the View tab itself. So back to the overview of the CFD process, I'll refer to this quite a bit. But within Helix, we're able to start with geometry import, go through surface manipulation, split surfaces, scale them, rotate them, turn them into different boundary conditions, create cell zones. Then we move on to mesh setup, simulation setup. We can actually launch and perform the simulation directly from the graphical user interface. And then we can do post-processing within the View tab to obtain results. Some of the key strengths of Helix are that it's a single cross-platform simulation environment. Cross-platform meaning it works on Linux, it works on Windows. It also has advanced meshing and physics incorporated into it. And because everything behind the GUI in terms of solvers, applications, so meshing, because that is open source, scale up and core count can be done without license limitations. So there's no parallel licensing with the applications in the background. For the same reason, scale out to unlimited simultaneous jobs is also, it doesn't require any parallel licensing. So if you are in automotive or you're in some other industry that requires many different simulations, and you have lots of HPC or compute capability, then you can really scale out and scale up your simulations to be able to achieve lots of throughput to help in the design process. And then finally, there's a Python macro for automation. And this Python macro, I did a webinar earlier in the year on how to use this, how it's set up, how can we record journals while we're using the GUI, and then we can automate this process and do a lot of meshing, setup, solving within the Python macro itself. One of the great things about, well, before I jump into that, so within the HELYX View tab, there's several different components. The first and foremost, the tabs. So these different tabs represent different stages within the CFD analysis process. So we have meshing, setup, solve, and primarily I'll be talking about the View tab. Within each tab, there's a ribbon interface, and this ribbon interface contains different objects, different widgets that are different actions that users can take on data or within this environment. There's also a tree and data panel. The tree is meant to help organize the information, and the data panel, this region right here, is where we actually interact with these different entries. So we can do things like configure boundary conditions or configure visualization aspects, things like that. And then next we have the viewport. The viewport is where we actually see scenes, or we see the data, we see the simulation results in three-dimensional form. Well, four-dimensional form if we include time. Within the View tab ribbon interface, there are things called objects. Objects are data filters. And again, slices, clips, streamlines, vectors, data threshold, isosurfaces. These are different objects that are currently available within the View tab. Here's just an example of streamlines from a simulation, and also again from an earlier webinar that I did earlier this year. Now, one thing that is a little different, and there's this concept of groups. So groups are collections of objects or mesh entities or geometric entities in which we use these lists of these different entities and we build different groups. So here I've got two selected surfaces, inlet and inlet duct, and I'm putting it together in a group called My Amazing Group. And here's another one where I have one called package space that have different sources, and we actually configure the visual representation of these groups. Now, the good thing about that is that if we have a massive amount of different entities, like different surfaces, we can control opacity, we can control what's actually being colored on the surface. So we may want the actual near wall velocity on the rest of a vehicle, but then we actually want the wall velocity on the wheels because the wheels are rotating. So we'd be able to group the wheels in one visual representation, and then we'd be able to group the rest of the vehicle in another different visual representation. Next, we have scenes. Scenes are used to present a perspective. And this is a way for people to kind of organize their data. And scenes are made of items, so groups, objects, mesh entities, geometric entities, color legends, so we can scale them, change the color, camera options for point, scale, focal point, or position, scale, focal point. And then finally, view options like background color, gradients, whether we display axes or if we display a logo. So it's a way for us to really kind of change how the image will look if we were to save this image. So one of the strengths of having scenes, you can see that right here, I'm applying a scene to a particular view. I've constructed these ahead of time, but by applying to a view, it snaps to something that's already been configured. And the benefit of this is that if I rerun this simulation on a finer mesh, or I extend it, the time scale, or change the end time, then I'm able to consistently get an image from the exact same angle from that same simulation. And then if I clone this case and I rerun it on different configurations, I can keep the same scale. So it allows us to have one single environment to go from meshing all the way to view, to be able to have the same images every single time. And I think as CFD engineers, we have to have a little bit of OCD to obsess about having the pictures and different angles to be almost exactly correct, to be able to really visually compare things together. This is especially important for multidimensional data. For things that are on plots, we can obsess about that in one way, but for multidimensional data, it's very helpful to have the same focal point, the same camera position, the same scale of different things, the same color scale, the same color kind of pattern. And this allows us to really organize that in one single environment. Okay, so I've talked about data analysis, I've talked about primitive and derived data and about how we can actually achieve this. And there's some features within inside of Helix and Elements to generate this while we're simulating. I've talked a little bit about probe data, integral data, and multidimensional data, and tried to tie the multidimensional data into the HELYX View tab and about how we can organize this really complex information into a particular perspective. Now, back to our CFD analysis overview. For a process that uses runtime visualization, instead of dedicating a lot of our time at the very end loading these very heavy, cumbersome data sets to obtain results, we actually go through this process, and before we simulate, we'll set up our runtime visualization. That way, while we're simulating, we'll be able to instantly go to our meaningful end result. So if we spend all this time making, plotting vorticity or, making these nice three-dimensional plots, our impatience will be satisfied by us seeing these different images as we're running the simulation. So it allows the users to output images of these scenes without writing the data itself. So without writing out all the velocity, pressure, and everything to memory, we're able to dump out these images. It actually leverages ENGYS's VTK developments used directly by the GUI. It works in parallel and can run simultaneously with the simulation. So to set up these runtime visualizations, really it's, once we have a simulation mesh set up, all of our solver settings, that's before we even get to this point. Next, we would set up a scene. We would configure it exactly how we'd like it to look. Then we would go back to the setup tab and we would go to this write data images interface. And really all we have to do is include whatever scenes we want to write. Then we control how often that image is going to be written, start time, end time, some of our information about the images that are being output. And then from there, we actually just need to run the simulation. And in that case, we can then take all that information and we can generate individual snapshots over time, or we can make a video of that particular scene over time. Here's just an example. So a few years ago, I made a really nice image of, while I was doing some testing during some developments. And this case was a 3D backward facing step at a Reynolds number of 125,000. So here we have 5.2 million cells. This is on 8 cores. It's using a transient K omega SST DDES model. There's a mapped inlet condition from a steady state flow. So there was a channel. We averaged that velocity in the channel coming into this backward facing step. The delta T is 1e to the minus 4, and the total simulation time was around 0.25 seconds. In terms of imaging, I wanted to collect 10 isosurfaces of vorticity from 1 to 10,000, and then take those isosurfaces and color them by velocity and omega from the K omega SST. So here on the left, we are able to capture these isosurfaces of vorticity that are generated, and we see some shedding of these vortices at the top of the domain. And then at the beginning of the simulation, you saw a little bit of vorticity generated from this wave of flow coming through the simulation. So we can see this turbulence being generated at the trailing edge of this backward facing step. If we were to actually zoom in on this area right here, looking down upon it, we can see this right here is colored by omega from K omega SST. So we're able to capture lots and lots and lots of different frames. Now this is just very colorful and it looks very nice at this point. There are practical applications that we can actually analyze this image afterwards. If we have two-dimensional data, then we can go further and we can compare different two-dimensional slices using other libraries. If we were to actually write all of this data, so 8 processors, it was 125 megabytes each time step on each processor. And there were 434 time steps. If all the volume data required to create these images in something like the View tab or in ParaView, it would be about 423 gigabytes of data. However, using runtime post-processing, so I've got 3 scenes, there's 434 images a piece, it comes down to about 507 megabytes, which means it's about 0.495 gigabytes of images, and it was a 99.88% reduction in data. And I mean, when I first saw this and did the calculation, it's a small case. But these kinds of savings, maybe not as dramatic, but we can definitely see a huge amount of savings if you're interested in three-dimensional images and slices of transient data. It's a tremendous amount of savings. Tremendous. I mean, this took me one night, and I was able to run this very easily and set this up to get a nice image for these different visualizations. Just some other examples. Here we have an Erkoftak centrifugal pump. This was a transient case. We used this in our last webinar about the coupled solver. This was done in just a few hours because we wanted to see just exactly how this would apply to transient cases with sliding meshes, so we can see some very nice results. Here on the right, this was to look at the transient wheel motion, so we can see the hubs in this sliding mesh actually rotating. Then we have a slice right at the hub height. Then we also have a slice down in the y=0. And we're looking at instantaneous velocity on those slices, but also instantaneous velocity on these near wall surfaces. So we can see a tremendous amount of information. We could have looked at averaged fields. We could have looked at different derived fields on this surface over time. So it was actually very interesting to be able to look at that. So the first question that people often ask is, oh, how does this scale? So if we took a case for automotive, this is very small. So 44 million cells on 64 processors. So the processors in this case are already overloaded with work. So there's around 687,000 cells for each processor. So I'd say this is kind of a atypical overloading on the processors, and we really wanted to kind of stress it just a little bit to see if we could get some interesting numbers. On time steps that had image output, so this wasn't necessarily writing an image every single time step, but on time steps that had image output, there was an additional cost. Not a surprise. The cost of the first scene was the most expensive. So here on the x-axis, we have the number of scenes that are being written on that time step. So we see a cost of the first scene from a time perspective was the most. And then subsequent scenes are less costly, and there was a relatively linear relationship. But the real cost of these different scenes really depends on the composition. I wouldn't say that a slice, if scene 1 was just something very simple versus scene 2 had 500 different isosurfaces, I would expect the cost between scene 1 and scene 2 to be very different. In this case, scenes 1 through 4 had very similar composition. So what is actually the estimated cost changing the write frequency of these 4 scenes? So let's take a look at it. So if we're taking 10,000 transient time steps and we don't write at all, if the time step is around 8.5 seconds per iteration, we should see about 23 hours for that simulation. If we write every single time step, we see for those 4 scenes, so we're writing 4 scenes, 4 images at every single time step, we see a pretty large jump in the total time. So basically doubling. So we're going 95% additional time. However, if we change our write frequency to 5, okay, now we see something a little bit more reasonable. Now we're in the 20-something hour range, every 10, every 50, every 100. Now we're only writing 10 images, and really it's just an additional time of minutes. So in reality, if you only write 1 image, it's really very cheap. And we might save ourselves additional time of waiting in line on each PC, if you have to submit another job afterwards to get back in line, or maybe you have to redistribute your case on a different number of cores, all of that adds to the total time of the simulation. So if we're looking at something like writing every 10 time steps, that's 4,000 images. And if you take those 4,000 images, it's actually about 3 minutes of video at 25 frames per second. So really, this is even overkill. We could go even further and get a lot of valuable information and really not pay a lot in terms of computational cost. One of the other strengths of runtime visualization is that there is Python API support. So we're able to create these complex scenes. We can automate image creation on a massive scale. So for example, if you create one slice of image or one slice of one image and you configure it exactly how you like, then you can record a journal during that process. And then potentially you could turn that into a function. You could pass that to automate this whole creation of different scenes. And then you could feed that into runtime visualization so that you would be able to have all these images along the length of the vehicle or width of the vehicle or the height of the vehicle. You could also do this on many different vehicles and say do image analysis of these results with third-party libraries. So this is the strength of using a Python library. And within the Python API, even though that Python API is interacting with HELYX or Elements, you can still have third-party image analysis libraries or third-party libraries interacting with that Python script itself. Okay. Now, some take-home messages. In general, post-processing really enables us to find qualitative and quantitative patterns in complex simulation data and allows us to really more effectively communicate with the right approach. And I think communicating with the right approach, I have right in quotations because I think oftentimes we'll have images and overload. This is where CFD represents coloring for directors or color for directors. If we use the right approach, then we can communicate effectively. And it also allows users to really convey a way of thinking about problems. However, post-processing comes at a cost. I say here that post-processing results are space filling. We tend to really take up all the space that we have on our hard drive, or all the space that we're allowed to get these amazing pictures sometimes. And we also have an attachment to our data. I don't want to say data hoarding, but we definitely hold on to our data if we've spent a lot of time on a project. Having something like runtime post-processing actually allows us to continue that bad habit, but save a lot less data. So, and also post-processing as an afterthought is really expensive and time consuming. So planning is really key to this whole concept of saving time and space. Is you just have to plan ahead. So runtime visualization can be economic and help us be more responsible, but still be able to hold on to some old results. In terms of the View tab, it really enables users to present data directly within HELYX, and scenes, it helps us create scenes to present a perspective and convey a message. So I think as CFD users, maybe we're using a more academic code in the past, and it was very time consuming to really set up visualization. So I think over a career of being used to that kind of thing, we really neglect the idea of going to something more complex. We don't want to do that because it's perceived as time consuming. So with runtime visualization and with scenes, we're able to actually lower those barriers of setting up these complex visualizations. So with runtime visualization, with planning, we can save a huge amount of data. In the example that I showed, it was 99.9%. Okay, that was an extreme. There's something in the middle that is still very significant. So I invite you to talk to me and talk to ENGYS about what features you're actually looking for. So what kind of filters are we talking about rendering? Are we talking about other data output to other software? I'm interested to hear exactly what people are concerned about and what they would like to see in their day-to-day operations. And then I'll go back to the original quote. So we tend to optimize effort and value. And if more descriptive simulations were easier to obtain, we would actually rely on them more. And so I think that we're able to get more descriptive information out of simulations with the View tab, with runtime visualizations now, which make them more valuable. And I think that at least internally at ENGYS, we use this quite a bit now, and our customers are finding more and more value in that, in using runtime visualization to save time and still be able to generate valuable information for the design process. Before I go, I would like to kind of plug an event that we're hoping to host in 2021. So the ENGYS user group meeting here in the US, it's in Detroit. It's a beautiful venue. I think it was the last trip that I took in the US before the lockdown happened. It's in Detroit, Michigan. You can visit ugm.engys.com. You can look at an agenda forming, and you can also register to keep up to date on any of the changes in the agenda or the location or anything like that. And with that, I think I'm good, and I will take any questions.